Welcome and thank you for joining us today. I'm Ricardo Camacho, Director of Product Strategy, Embedded Safety, Critical and Compliance at Parasoft. Today we're excited to present on integrating GoogleTest in safety critical systems with confidence. I'm here with my good friend and colleague Miroslav Zielinski, Director of Product Management for C++ Testing Solutions. Mirek, would you like to say hello?
Hello, everybody.
Thanks, Merrick. And as always, it's a pleasure doing these webinars with you. Now, today we're going to talk about the challenges in deploying the Google Test unit testing framework for test automation in development of embedded safety critical applications. We'll explore why Google Test is popular and discuss both the opportunities and the obstacles of using Google Test in safety critical environments. But first, let's dive into the agenda. First, I want to start with a very quick glimpse at functional safety and how unit testing relates to mandatory verification and validation requirements. I'll then jump right onto Google Test, what it is and why it's so popular, followed by extensions to Google Test that Parasoft provides. And this is related to compliance demands by functional safety standards. I'll then cover a very important aspect regarding tools used in development and testing of safety critical applications, which is certification. We also will get the pleasure of Mirek demonstrating an agile development workflow using Google Test and Parasoft's extensions. It's a fantastic demo, and I'm sure you're going to love it. At the end, we will open it up for Q&A. All right, let's get started. In regulated industries like automotive, medical, aerospace, rail, industrial automation, and others, you have functional safety standards that offer best software practices in ensuring delivery of products that are safe. You see some of those standards listed like ISO 26262, DO 178C, and the others. Now, I've put the very well-known V-model process image on the right that the standards live by, showing you the various phases in development, and each phase is very well documented, containing objectives that need to be performed so that you can ensure safety. You have requirements management and design phases on the left side of the V. Going through those phases, systems engineers gather requirements from the stakeholders or regulatory agencies, and through decomposing those requirements and performing hazard analysis and risk assessments along with design activities, hundreds to thousands more requirements are flushed out, to the point of having low-level requirements that you can then realize them or implement them by way of functions or procedures or methods. Anyway, the V model is not a software development lifecycle, it's a process. You have the option to follow a waterfall approach or use an iterative method or apply an agile mindset. But the crucial aspect on ensuring safety is the verification and validation objectives defined in these standards. I've listed several of them below. You'll see static analysis, structural code coverage, unit testing, requirements-based testing, which is, to me, one of the most important validation activities that you're going to need to perform. And I say this because at each phase of the V model, you see a horizontal line that connects the right side with the left side of the V. This means that requirements defined at that level need to be tested. That's why you have system level testing, integration testing, and unit testing. And there's a lot more detail defined in these functional standards like traceability, compliance reporting, having an audit trail, the production of specifications like your design spec, your requirement spec, your interface control documents, your test plans and procedures, and much more that we don't have time to go into. But what I want to bring out is the importance of tool certification. These functional standards define tool qualification requirements to help ensure that development teams use tools that won't introduce bugs into the workflow, that the tool's results are trustworthy, and that the tool is helpful, not harmful. This is a concern when using open source tools, and I'll get more into this later in the presentation. But let's get into unit testing and Google Test. Now, unit testing is a cornerstone of safety critical software development. In industries like automotive, aerospace, and medical devices, where functional safety standards mandate that the software be verified at the smallest possible level. However, this has gotten more challenging. Today, modern projects are far more complex than they used to be. We've moved from plain C to modern C++. We now integrate artificial intelligence and machine learning, and we have adopted modern CI/CD development workflows and pipelines that integrate tools like Git, GitHub, Jenkins, Bazel, Docker, Bamboo, and the list actually continues. And development teams often struggle with unit testing due to tight schedules, complex code dependencies, and difficulty isolating each function as required for embedded or safety critical environments. So, without proper tooling, test coverage can be inconsistent. Tests may not integrate smoothly into CI/CD workflows, and maintaining them becomes a huge burden as code evolves. Also, many developers lack the skills or time to create effective tests, and legacy code can be challenging to adapt for testing. Plus, these standards add the extra burden of traceability and documentation for compliance. So, these challenges can lead to gaps in quality, slower delivery, and higher project risk. But fortunately, unit testing frameworks like Parasoft C, C++ test, that we offer exist to make testing not only easier but also more reliable, automated, and compliant with industry requirements. They go beyond just letting you write and run tests. They integrate directly into your development workflow, automate test execution, measure and report coverage, and connect results back to requirements for full traceability. It offers mocking, stopping, and isolating hardware dependencies, making it possible to test complex systems without costly manual workarounds. And on top of that, C++ test is TÜV certified, so teams working under standards like ISO 26262, IEC 62304, IEC 61508, and EN 50716 can avoid lengthy tool qualification processes. Now, for teams working on safety critical software, GoogleTest offers a straightforward, developer friendly experience without the cost or structure that comes with a commercial, compliance focused solution like C++ test. So, if you're just looking to get started quickly with unit testing and don't have heavy compliance requirements, you might just lean towards using GoogleTest. Now, GoogleTest is free, open source, lightweight, and has a low barrier to entry. It's easy to set up, intuitive to use, and well documented with a huge community for support. It integrates smoothly into most build systems and CI/CD pipelines without much configuration, and you can, be writing successful tests in minutes. So, for teams working on non-safety critical software or those who prioritize flexibility and minimal overhead, GoogleTest offers a straightforward, developer-friendly experience without the cost or structure that comes with a commercial compliance-focused solution. The big draw is its flexibility and modern C++ API, featuring rich assertions, reusable test fixtures, and parameterized tests to cover a wide range of scenarios efficiently. Also, its strong portability and integration capabilities allow cross-platform support and seamless connection with IDEs and CI/CD systems, ensuring it fits naturally into modern development workflows. So developers appreciate its simplicity and efficiency with clear syntax, informative error messages, and fast execution that streamlines the testing process. Now, Google Mock is included as part of GoogleTest, which further enhances flexibility by enabling effective mocking for complex dependencies. But this freedom does come at a cost. GoogleTest doesn't include built-in automation for generating test cases, And it doesn't come with tool qualification packages, which are critical in safety critical projects. So while the technical team may love its use, the compliance team is going to have some questions. And this is a dilemma that we see out in the field. Many organizations have extensive existing GoogleTest code bases and developer experience invested in it. So we have made a decision at Parasoft to support these organizations where they already are. So we want to remove barriers for these teams so that they can satisfy compliance with their safety critical standards. And it gives us the opportunity to provide value and maintain relevance in these diverse development environments. So we began by enhancing GoogleTest with verification capabilities required for safety critical development. This includes code coverage, requirements traceability, and automated report generation. TÜV certification is currently in progress, expected in Q4 of this year or early next year, so 2026. Now, these verification enhancements have been released under the product name C++ Test CT, and it has been TÜV certified, so you get compliance-ready testing while leveraging GoogleTest infrastructure. Now, Parasoft C++ Test CT is a versatile, again, TÜV certified testing solution designed for modern C and C++ development workflows. It features a 100% IDE independent command line oriented toolchain, making it highly suitable for automation at scale and integration into CI pipelines. And as I mentioned, it's designed to integrate with GoogleTest, but also with other testing frameworks like CPP Unit and Boost Test by enhancing their capabilities, particularly for safety and security critical compliance driven development. So it doesn't replace these frameworks, but rather works alongside them by providing additional features. And I'll get to that more detail soon. But C++ Test CT also offers a container-friendly architecture to enable seamless deployment across diverse environments, and it supports on-target testing to validate software in real hardware conditions. And with dedicated build system integration for CMake and Bazel, C++ Test CT ensures smooth collaboration with existing build processes. Developers can also benefit from a powerful VS Code extension, allowing tests to run efficiently both on their desktop and in a continuous integration system, combining flexibility, compliance, and developer productivity in a single solution. But let me quickly give you a glimpse of some of these CT extensions. As you know, in software development, structural code coverage is a critical metric for gauging the thoroughness of a test suite. It helps developers determine which parts of their code base are being executed by tests and which ones are not. I believe you're going to see how it's integrated into the CI pipeline via the command line interface, so I'm not going to go into those details. But as you can see on the bottom right corner of the slide, code coverage metrics like statement, branch, and MCDC coverage is correlated in the C++ Test VS Code extension. Additional value lies in not just the ability to pinpoint untested lines of code, but we provide clear, actionable feedback to improve code coverage gaps and enhance your test suite. Merrick will actually include this in his demo. There's also some screenshots of HTML code coverage reports that are being published in GitHub pages, which you will also see in the demo, making it easy for the entire team to view the results. And for more advanced analytics and centralized reporting, our solution integrates with Parasoft DTP, which is our web dashboard, and it provides a single source of truth for all your quality metrics. And finally, a crucial point for developers is that our solution is not tied to GoogleTest, in case you're wondering. C++ Test CT also integrates with many other open source frameworks like CPP Unit, Boost Test, and even with homegrown frameworks. So if you're using some homegrown custom framework out there, talk to us because we can integrate our extensions into your development ecosystem. Also, as I mentioned before, in safety critical development, it's not enough to write and run tests. You have to show exactly which requirements they satisfy. That means linking each requirement to the code that implements it and the test that verifies it. And the integration with Parasoft DTP enables bidirectional traceability and navigation with ALM tools like Jira, DorsNext, JAMA, Codebeamer, and Polarian. You're going to see actually Merrick demonstrate this with Jira. Now, GoogleTest is a powerful choice for modern C++ projects thanks to its flexibility and seamless fit within complex development workflows. But in safety critical industries, compliance is not optional. To achieve it, GoogleTest must be extended, qualified, and continuously maintained, an investment in both process and people that ultimately ensures long-term efficiency and scalability. So Parasoft has committed to certifying GoogleTest. Its release is scheduled for the end of the year, but it could slip into early 2026. But it's going to be a very big breakthrough. Qualifying an open source framework is no small feat. There are no predefined requirements to inherit. We created them, validated them, and ensured that they meet the rigorous standards demanded by safety critical development. The result is going to be a version of GoogleTest that you can trust, not just for test execution, but for compliance, reliability, and risk reduction. It's a rigorous effort, and I believe it's also going to be a disruptive move in the testing landscape, but a commitment that we're very proud to stand behind. Okay, so let's get to the fun part. I'm going to hand it over to you, Merrick.
Thank you, Ricardo. In this demonstration, we'll show how to provide evidence for achieving code coverage goals from GoogleTest-based unit testing and how to use Google test cases for requirements testing. Let's see it in practice. Our demo project is based on a popular open source library for inter-process communication. In our design, we plan to use it in the autonomous driving system. Our project is hosted in GitHub, and team uses a modern CI-based development workflow with containerized toolchain and automated CI quality gates. For our code, we need ISO 26262 ASIL-D compliance. So far, in the early stage, project was developed with limited attention to standards compliance. Developers used GoogleTest to add unit test cases, but the process was not systematic, code coverage was not monitored, and testing was not traced to requirements. For our next compliance milestone, we have two goals. We want to start monitoring statement and MCDC code coverage metrics for the newly created code, and we want to start tracing relevant tests to requirements. With Parasoft C++ Test CT, integrating code coverage into project builds is easy. There are dedicated integration packages for build systems such as CMake or Bazel. The tool is also very easy for containerization. To integrate the tool for our demo project, we need a small insertion in the CMake list file and a corresponding configuration file. With this change, our build targets are now extended with code coverage monitoring, and we can move on to implementing new features. Let's say our task is implementing the emplace method for a vector class. We do have a set of low-level requirements for this new code. As a developer, I've analyzed the specification and implemented the first version of the emplace method. I've also added a first couple of unit test cases. Please note that my test cases are correlated with requirements via dedicated properties injected into test cases. This correlation establishes a test2 requirement link that enables C++ Test CT to generate requirements traceability reports mandated by all safety standards. Now I'm interested in whether my tests pass and the code coverage level for my newly implemented code. Let me build the project, run new tests, and generate code coverage reports. As you can see, the code was built and tests were executed. As a part of the build process, C++ Test CT generated code coverage reports. C++ Test CT generates reports in multiple formats, including raw text, machine processing friendly JSON, and HTML. For developers, the VS Code extension is probably the most convenient way to analyze the results. Let's enable line coverage and look at the new code we added. As we can see, we do have some code coverage, but our basic tests examined only a part of the implementation. We need to add more test cases. We can derive additional test cases by requirements analysis. Let's add a few more tests, ensuring they are linked to appropriate requirements. And execute them. We expect coverage for the emplace method to increase now. And indeed, it seems we now have 100% line code coverage. We are now ready to push the code to the repository. And create a pull request. My pull request triggered the automated pipeline. The pipeline goes through several stages, including code coverage quality gate. Let's take a look at our pipeline definition while it executes. Here, the code coverage tool is enabled for the build. No other actions are required for the integration. Our default target includes building GoogleTests. Here we execute binaries with unit tests, and here we invoke report generation targets added by C++ Test CT CMake extension. Once the report is generated, it's published to the GitHub pages so that the team can easily access it. Below are code coverage quality gates for statement and MCDC coverage metrics. Our current requirements for the quality gates are 100% statement and 90% MCDC code coverage for the new code. Let's go back to our pull request and see the pipeline result. It failed. It seems we have a problem with MCDC coverage. Our line coverage quality gate passed, but the MCDC coverage quality gate has failed. We simply did not achieve expected 90% of MCDC coverage for the new code. To understand the gaps, we can review the HTML report published on GitHub pages, or what may be more convenient for developers, we can view results using VS Code extension. C++ Test CT VS Code extension integrates with GitHub and automatically downloads the most recent results for the working branch. We can now analyze why our MCDC coverage quality gate failed. Let's see MCDC results for the method we are implementing. We have 3 decisions in the method. For 2 of them, we have achieved 100% MCDC code coverage. However, we still don't have the complete coverage for the first decision. Let's take a closer look. C++ Test CT provides extended MCDC coverage reporting that helps understand coverage gaps. In our situation, we have 3 conditions in the decision. The second and third conditions are already covered according to MCDC coverage requirements. we still don't have the coverage for the first condition. Here we have a list of test vectors that were executed as a part of our testing process. It includes information about the values that conditions were evaluated to and the outcome of entire decision. Below, we have information about missing test vectors. A great value is that the tool computes the minimal set of test vectors required for the complete coverage, helping developers to be more productive. In our case, we need a test vector to evaluate the first condition as true. It means we need a test case that tries to emplace an object at the position exceeding current capacity. Let's add this test case. In general, depending on the situation, different actions may be required to eliminate the coverage gaps, including changes in implementation, modification of requirements, and addition of missing tests. In our case, the code was correctly implemented following requirements, but the developer forgot to add a test case for a specific scenario. The problem was detected thanks to C++ Test CT based quality gate. Let's make sure our new test case is correlated with appropriate requirement, and now we are ready to push the code again. This operation triggered a pipeline for our pull request. Let's give it a minute to finish. Alright, it seems our coverage quality gates passed, and we are now ready to merge the code into master. For the master branch, we have a dedicated pipeline verifying integrated code. This pipeline executes extensive set of tests and monitors the code coverage for the entire project. Our merge operation triggered this pipeline. The results of this pipeline represent the current status of our stable branch. Our master pipeline sends the results to Parasoft DTP, the reporting platform. Parasoft DTP aggregates results from different types of testing and presents results in graphs, trends, and compliance reports. With these widgets, I can monitor my progress in various compliance aspects, including the progress with the code coverage. I can also check the progress with requirements implementation and testing. With this widget, I get information about the number of requirements already covered with test cases and those that are not, and require attention. This information allows me to react if my progress with compliance goals, including code coverage, is too slow. This kind of insight is essential for any persona involved in the safety, security, or quality process management. And this is the end of our demonstration. Let's recap. In our demo, we presented a CI-based workflow where C++ Test CT was used to satisfy coverage and requirements traceability reporting objectives stemming from the safety standard. In our demonstration, the development toolchain including C++ Test CT was containerized and used for CI pipelines and at the developer's desktop. We have gone through the following sequence. Developers started working on a new code in the feature branch. Here, C++ Test CT was used on the developer's desktop. Then the pull request was created where C++ Test CT was used as a coverage quality gate. On the first attempt, code was rejected and the developer downloaded pipeline results to the local IDE for a remediation. After applying fixes, code was successfully merged. For merge code in the master branch, another pipeline was executed. The master pipeline results were sent to Parasoft DTP for trends and compliance status analysis. Ricardo, this is the end of our demonstration.